Welcome back. Let's look at the fourth example problem, root mean squared error of predictions. In this problem, we have Alice and Bob, who each have a formula for predicting housing price using 5 pieces of information: the number of bedrooms, square footage for first floor, square footage for second floor, number of full baths, and number of half bathrooms. You are asked to calculate the root mean squared error, or RMSE, of the predictions based on the two formulas. So the meaning of root mean squared error should be explained backwards. So let's first look at error. So error means the difference, or the absolute value of the difference between the predicted price and the actual price. So in the input data, we have the true price of the house. So based on prediction, then we can compute the error. So squared error is just the error squared. And mean squared error means when we compute when we have n houses, we will compute the squared error for each one of them, and then we compute the average of the squared error. And the root mean squared error means that we then take a square root of that mean squared error. So root mean squared error is a concept that is commonly used in machine learning for prediction, so measuring prediction accuracy. And in this problem, the output is required to be printed using 2 decimal places. So here is one set of sample input and output. So the data are actually coming from a website called Kaggle, which run machine learning competitions and also have many data sets. So for each house, the first is the price of the house, number of bedroom, first floor footage, second floor footage, number of full baths, and number of half bathrooms. And the sample output is the RMSE from Alice's prediction and that from Bob's prediction. And also we are asked to print this line. If Alice's error is less than Bob, we will say Alice's RMSE is certain percentage of Bob. If Bob is less than Alice, we will say Bob's RMSE is certain percentage of Alice. So the logic of the code is fairly straightforward. However, we do need to introduce some new concept to deal with the requirement. For example, to compute square root, we use a predefined function. So in the library, and the definitional function is in the header file CMath. And to print with 2 decimal places, we need to use features that are defined in the IO manip, which stands for IO manipulation in that header file. So in the code here, I used 2 functions for computing the predicted price from Alice and from Bob. So this is not strictly necessary because this prediction formula is actually used only once. But here I just put them in a function in part to show that you can use function to do that. And also I felt that because the formula is kind of important thing, so having it stand out as a separate function seems to be slightly better. So this is the second part of the solution code, and there's a third part which we'll explain later. And here we introduce some new concept. So for example, because the calculation will no longer be all in integer, when we take a square root, the number will not necessarily be integer. So we use a new data type called the double to represent these real numbers. And we also use this function square root to compute the square root. So the other part, the logic is fairly straightforward. For each house, we read in the data, and then we compute the error for using Alice's prediction, and then we compute the sum of squared error for Alice, and then we compute Bob's error, we add that to the sum, and in the end, we compute the average and then take square root. So to represent real numbers, C++ has a few new data types. So float stands for single precision floating point type. So real numbers are known as the floating point type. So we will not, in this course, we will not talk about how exactly floating point the number are represented in computer. But all data are stored in computer using binary. Binary means that it's base 2. So when we represent number, you only have 0 and 1 digit. So we are more commonly familiar with base 10. So you have a digit from 0 to 9. But actually, even in real life, we use other bases sometimes. For example, 1 foot has 12 inches. 1 pound has 16 ounces. So typically in C++ implementation, int will be 32 bits. So it's represented by 32 binary digits. And as a result, this is a range that can be represented using int types. So it's roughly 2 times 10 to the 9. And this number is because this is from negative 2 to the 31 to positive 2 to the 31 minus 1. So there are exactly 2 to the 32 different numbers in this range. And floating point number in typical implementation using also 32 bits, but they use some of the bit to represent an exponent. So you can think of the scientific notation of numbers, where you have an exponent and then you have a number, sort of a base number. And because of that, they can represent much bigger numbers, 10 to the 38 instead of 10 to the 9. And the double use 64 bits in the typical implementation of C++ today. So they can represent even bigger numbers. And the long double is also a C++ type, but its implementation hardware dependent. So it could use either 64 or 80 or 128 bits, depends on the hardware and the compiler implementation. So my suggestion is when you need to use a floating point number or real number, just use double. So the square root function we use is defined in CMath. In fact, there are multiple versions of them taking different input types. So in summary, unless the input is if the input is floating, is a float type, then the output will also be float type. If the input is long double, then the output will also be long double. For any other type, for example, if you use an integer you call square root, then you will get a double as the result. The CMath header file defines other functions, so this is only a small subset of it. So these are the ones that are more likely to be used in introductory programming. So absolute value, ceiling, floor, so rounding x to integers, and the max of 2 numbers, a min of 2 numbers, and power, raising x to the power of y. So this is the final part of the code for this problem. I think the logic is pretty straightforward. The only thing that's really new is this fixed and set precision thing we use for the cout stream. So we use that to print with a fixed number of decimal places. And they are defined in the header file IO manip, which stands for IO manipulation. So fixed means that it will tell the cout stream when you print floating point number, you print it in a format that will fix the number of decimal places. So the number of digits after the decimal point. And set precision tells the how many decimal places we want. So by using this, we are printing output that has exactly 2 decimal places.